Okay, so you know that feeling when you stub your toe?
Yeah.
That, like, really sharp pain from just one tiny spot.
Oof. Yeah. Definitely know that one.
It got me thinking, why does that hurt way more than, say, just leaning your whole body weight against a wall? I mean, it's still you, still force, sort of, but the ouch factor is completely different.
Uh-huh. And that difference, that sensation, it actually points to something really fundamental in physics.
Right, and that's what this deep dive is all about. Pressure.
Exactly. We've looked at some really good explanations, source texts, everyday examples you'll recognize instantly, and even crunched a few numbers.
Yeah, just to really nail down what pressure actually is.
And maybe more importantly, why it matters so much in the world around us.
Absolutely. So our mission here, for you listening, is to really get an intuitive feel for pressure, not just, P equals F over A.
Though we'll get to that.
We will.
Eh.
But it's about understanding how it works, seeing those invisible forces. Think of it like getting pressure vision superpowers.
Ah, I like that. Okay, so first things first, we got to talk about force.
Right, step one.
Our sources define it pretty simply. A push or a pull. Something that can, get an object moving or stop it or change its direction.
Like opening a heavy door, you need force for that.
Or kicking a ball, yeah. That interaction, that's force. Pretty straightforward.
Okay, makes sense. But here's where it gets more interesting, right? That same push or pull, the same amount of force, can have totally different effects.
Exactly. Think about the example in the materials, a person standing up versus that same person lying down.
Their weight doesn't change, right? Gravity's pulling on them just the same. That's the force.
Correct. The force, their weight is constant, but what is changing?
Well, when they're standing, all that weight is on their feet. Pretty small area.
Uh-huh.
But lying down, suddenly it's spread out over their whole back, legs, everything. Much bigger area.
Bingo. And that difference in how the force is distributed over an area.
That's pressure.
That's pressure. It's not just the total force, it's how concentrated it is.
Which brings us nicely to the formula they give us. Pressure, P, equals force, F, divided by area, A.
P equals F over A. Simple but powerful. Pressure is just force per unit area.
Okay, so looking at that, P equals FA. There are two main ways to change the pressure, right?
Yeah. Two levers you can pull. What's the first one?
Well, the force itself, F. If you push harder, increase the force.
Keeping the area the same.
Right. Same area, more force.
Yep.
You get more pressure. Like really leaning on that thumbtack to
Right.
get it into the board.
Exactly. More force, more pressure. What's the second lever?
As the area, A, the denominator.
Uh-huh. What happens if you keep the force the same, but change the area, like our person standing versus lying down?
Well, if you make the area bigger, like lying down, you're dividing the same force by a larger number.
So pressure.
Goes down. Less pressure.
Perfect. More area, less pressure for the same force.
And they had that great visual in the source material, Activity 1, with the iron blocks in the mud.
Oh yeah, that's a classic demonstration. Really simple, really clear.
Explain that one.
Okay, so you take an iron block. It has a certain weight, right? That's our force.
Okay.
Now, you stand it on its end in some soft mud. That end has a pretty small area. What happens?
It sinks in quite a bit.
Right, because the pressure is high, same force, small area. Now take the same block, same weight, same force. But lay it flat on its side in the mud. Much bigger area touching the mud now.
And it won't sink nearly as much. Or maybe not at all.
Exactly. Same force, larger area, much lower pressure. So it doesn't sink as far. It really shows that area effect.
It's neat how we actually measure this stuff. So the unit, it's newtons per square meter.
That's the standard SI unit, yes. Newton for force, square meter for area.
But it has another name too, right? Pascal?
Yes, named Pascal, PASU short. 1 Pascal is 1 Newton per square meter. We often use kilopascals, kTA, too, because, well, 1 Pascal is actually a pretty small amount of pressure in everyday terms.
And Pascal. That's named after Blaise Pascal. Why him?
Ah, Blaise Pascal. He was, a brilliant mind back in the 17th century. Scientist, mathematician, philosopher. He did fundamental work on how pressure works in fluids, liquids, and gases.
Like atmospheric pressure.
Exactly. His experiments and insights were crucial. So, yeah, very fitting the unit's named after him.
Okay, let's connect this to stuff we see all the time. Yeah. Everyday examples. Why does stepping on a Lego brick barefoot feel like actual torture?
Oh, the Lego. The ultimate pressure test.
Right. But if you step on it with a shoe, it's fine. What's the physics there?
It's all about that area again, the little studs on a Lego brick, tiny surface areas.
Yeah.
So when your barefoot hits it, all your weight, the force gets concentrated onto that tiny point. Boom. Really high pressure, hurts like crazy.
But the shoe.
Your shoe sole is flat, much larger area. It spreads your weight out, distributes that force, so the pressure on any one point, even right over the Lego stud, is way, way lower. Doesn't hurt.
Ouch. Oh, okay, that makes painful sense.
And it's the same reason a sharp pin goes into, say, a notice board easily. But a blunt nail is much harder, even if you push with the same effort.
Precisely. The pin's tip is incredibly sharp, meaning a minuscule area of contact.
Right.
So even a small force from your thumb creates enormous pressure right at the tip, enough to push through the material, the blunt nail. Much larger area at the tip. Same force gets spread out, lower pressure, harder to push in.
So sharpness is really about minimizing area to maximize pressure.
You got it. That's the principle behind all cutting tools, isn't it? Knives, scissors, axes, they all have a very thin, sharp edge.
Tiny area of contact.
Which means the force you apply creates immense pressure along that edge, allowing it to slice or split things.
Okay, so that's decreasing area to increase pressure. What about the opposite? Increasing area to decrease pressure.
Yeah, loads of examples there, too. Think about those huge, heavy trucks on the highway. Why so many wheels?
More wheels means more tires touching the road. Right, more contact area. Yeah. That truck weighs a ton, massive force. But by spreading that weight over, say, 18 wheels instead of 4...
You lower the pressure on any one patch of road.
Exactly. Reduces wear and tear on the road, prevents the truck from just sinking into softer surfaces.
Okay. What about animals? Like a camel walking on sand compared to a horse.
Great example. A horse has relatively small hooves for its weight. High pressure, sinks into soft sand.
Yeah.
A camel, though, has those famously wide, flat, padded feet.
Right. A big surface area.
Huge surface area. Spreads its weight out beautifully, much lower pressure on the sand so it can walk across the desert without sinking nearly as much. It's an adaptation.
And it's the same idea for skis, right? Or snowshoes.
Absolutely. You strap those long, wide things to your feet. Why?
Yeah.
To increase the area your weight is spread over.
So you don't sink into the snow. Lower pressure.
Lets you glide right on top. Without them, your boots would exert much higher pressure and you just post hole straight down.
Makes sense. And army tanks, those caterpillar tracks, they look like they'd be heavy.
They are incredibly heavy, but those tracks are super wide and long.
Massive surface area.
Massive.
Yeah.
So even though the tank weighs many, many tons, that force is distributed over such a large area that the pressure on the ground is relatively low.
So it doesn't get stuck in mud or soft ground.
Exactly. It can traverse terrain that wheeled vehicles of similar weight couldn't handle.
Even buildings use this.
Yeah.
Like the foundations.
Definitely. You don't see skyscrapers built on pointy legs, do you?
Huh.
They have wide, extensive foundations. Why? To spread the enormous weight of the entire building over a large area of the ground underneath.
Reduces the pressure on the soil.
Prevents the building from sinking or becoming unstable. Critical for structural integrity.
Okay, another one from the sources. Quarters carrying heavy loads, sometimes on their heads. They often use a cloth or a turban, right?
Yeah, that coiled piece of cloth, often called a pagri or just a head pad.
What's that doing?
It's increasing the area of contact between the load and the top of their head.
Instead of the weight pressing on just a few points.
It's spread over the larger area provided by the padding. Reduces the pressure, makes it, well, less painful and more manageable to carry heavy things that way.
And same idea for backpack straps. Why are wide straps more comfortable?
Same principle. A wide strap distributes the weight of the bag over a larger area of your shoulder.
Lower pressure?
Low pressure, more comfort. A thin strap concentrates all that weight onto a narrow strip of your shoulder. High pressure. Digs in. Feels bad.
Right. Simple when you think about it. And back to shoes. High heels versus flat heels.
The classic example, that stiletto heel. Tiny, tiny contact area. So even if the person isn't particularly heavy, the force of their weight concentrated on that point creates incredibly high pressure.
Which is why they can dent wooden floors, right?
Absolutely. Or sink into soft grass. A flat shoe, same person, same weight, spreads the force over a much larger area. Lower pressure, no damage.
Okay, so we've really covered the area part of the equation. Increasing it decreases pressure, decreasing it increases pressure. What about the other factor? Force.
Right, the F in P equals FA. What happens if we increase the force but keep the area the same?
Well, the formula says pressure goes up.
Yeah.
P is proportional to F.
Exactly. Think about hammering a nail. The nail tip has a fixed, small area.
Yeah.
Just pushing it with your thumb might not create enough pressure, but hit it with a hammer.
You're applying way more force.
A much, much larger force onto that same small area. The pressure skyrockets, and that's what drives the nail into the wood.
Okay. And what about underwater? Like when you dive deep in a pool and feel it in your ears.
Yes, that feeling is water pressure.
So the deeper you go.
The more water is above you, the weight of that column of water presses down.
More water means more weight, means more force.
And more force pressing on the area of your eardrum. So deeper you go, greater the force, higher the pressure.
And that's why submarines have to be built so strong, right?
Incredibly strong.
Yeah.
The pressure deep in the ocean is immense. They need to withstand enormous forces pushing in on their hull from all directions. Same for underwater tunnels. Designing for pressure is critical.
The sources also mentioned a word thrust. How's that different from force or pressure?
It's closely related. Thrust is basically the name we give to the force acting perpendicularly or, at a right angle to a surface.
Okay, so it's still a force, measured in newtons.
Still a force, still measured in newtons. The key difference is how it relates to pressure. Pressure is specifically the thrust per unit area.
So pressure, thrust area.
You got it. Thrust is the total push on the surface. Pressure is how concentrated that push is. Thrust doesn't care about the area. Pressure absolutely depends on it.
Okay, that clarifies things. Now, the sources had some calculations too, just to see the formula in action?
Yeah, they're helpful to make it concrete. Like example 1.
Yeah.
A solid block weighs 80 newtons. That's our force, or thrust.
Okay, 80 N.
And it's resting on an area of 1.6 square meters.
1.6 meters rounds.
So pressure, just divide. P equals FA, and 1.6 meters in area.
Which comes out to 50.
50 newtons per square meter, or 50 pascals, 50 pas, simple division.
Straightforward enough? And you can rearrange it too, right?
Yeah.
If you know the pressure and area, you can find the force.
Absolutely. Force would just be pressure times area, F real PA.
Cool. Now, there was that really striking comparison they made. The girl in high heels versus the elephant. That one really stood out.
Oh, yeah. That's a fantastic illustration of how much area matters. It often surprises people.
Break it down for us.
Okay, so they imagine a girl maybe weighs 500 newtons, standing on stiletto heels. The total area of those heels touching the ground is tiny, maybe just 2 square centimeters total.
Okay, 500 N force, 2 centimeter area, very small area.
Very small. Then you have an elephant, massive animal, weighs, say, 20,000 newtons. Huge force.
Much bigger force than the girl.
Way bigger, but its feet are also big. Let's say the total area of its 4 feet touching the ground is 1,000 square centimeters.
Okay, so huge force, but also a much larger area than the heels.
Right. So who exerts more pressure? You calculate it out, pressure, force, area.
For the girl, 500 N divided by that tiny 2 centimeter area.
Gives you a massive pressure. If you convert to pascals, it's something like 2.5 million pascals.
Wow. Okay. And the elephant.
20,000 newtons divided by 1,000 centimeters X. Still a big force, but over a much bigger area. The pressure comes out to about 200,000 pascals.
So, wait. The girl exerts more pressure? Like 10 times more?
Significantly more. Even though the elephant's force is way higher, the girl's incredibly small contact area concentrates her force so much more intensely.
That's actually amazing. It really shows it's not just about the force. That area factor is huge.
It's absolutely critical. It's often the area, not the force, that dominates the pressure calculation in surprising ways.
That's a real aha moment, isn't it?
Yeah.
Really brings the concept home.
Hopefully. And once you grasp that interplay between force and area...
You start seeing it everywhere.
Exactly. As you go about your day, you can spot these principles at work.
So let's kind of wrap this up. What are the absolute key takeaways for you listening?
I'd say the core relationship.
Yeah.
Pressure goes up if you increase the force or if you decrease the area it's applied over.
And conversely, pressure goes down if you decrease the force or if you increase the area. That inverse relationship with area is key.
Right. Force and pressure, directly related. Area and pressure, inversely related.
And knowing this isn't just, physics trivia.
Not at all. It explains so much about why things are designed the way they are, from shoes to tires to knives to buildings. It has real-world consequences.
So final thought to leave you with. Something to chew on. We've talked physics, but where else might this concept of pressure be super important?
Ooh, good question. Think bigger. What about engineering? Designing bridges, dams?
Or medicine. Blood pressure, obviously, but maybe pressure inside joints or cells.
How about meteorology? Air
Yeah.
pressure differences drive weather systems, right? Highs and lows.
Even nature. How do plants move water against gravity? Could pressure play a role? What other surprising situations are governed by this simple idea of force spread over area?
Lots to think about there. Next time you put on your shoes or see a heavy truck, maybe you'll see the physics a bit differently.